So previously we have discussed about the chapter 19 functions, and we have given a definition of a function in the previous part of this lecture in this chapter, and then we have given 6 examples of functions. Then we have discussed types of functions. So we have discussed one-to-one function, on-to function, and bijection function. Then we have analyzed like which of those 6 functions have what kind of type. So we have defined that. Also, we have solved that problem. Now we will give a criteria to identify which functions are of which type, and that we will do by defining a proposition. (19.1) says that let f is a function from S to T where S and T are finite states. Number 1, if f is onto, then order of S is greater than order of T. Okay. If f is 1-to-1, then order of S is less than order of T. 3, if f is bijective or bijection, then their order is same. Let's give a proof. Okay, number 1, we say that let order of S is n, and write that S has n elements. As f is onto, we have that T is equals to f of S, which is nothing but f, the set which contains the images for every Si to Sn. Hence, order of T is nothing but less than or equal to n. Okay. Of course, order of T could be less than n, as some of the Fi's could be equal. Okay, number 2. Let order of S is n, and S is the set of Sn elements. Now, is f is 1-to-1 into the elements f of S1 up to f of Sn are all different and lie in T. That means Therefore, order of t should be greater than or equal to n. Number 3, if f is a bijection, then we have both inequalities. So their order is same. This is the proof. Okay. Now you can see the part 2 of this proposition implies that over here that order of t is greater than or equal to n, where n was the order of s. So if order of s would be greater than order of t, then there is no one-to-one function from s to t. And this can be phrased somewhat. So this is just a remark. So I'm going to write that in a different pen. So part 2 of proposition 19.1 implies that if order of s is greater than order of t, then there is no one-to-one function from s to t, and this can be written as the following. So if and we note that by a principle, let's call that pigeonhole principle. Pigeonhole principle. Which says that if we put n plus 1 or more pigeons into n pigeonholes, then there must be a pigeonhole containing more than one pigeon. Okay. Now, if no pigeon contain more than one pigeon, the function sending pigeons to their pigeonholes would be one-to-one. The above statement is the pigeonhole principle, and it is surprisingly useful. As a very simple example, in any group of 13 or more people, at least 2 must have their birthday. in the same month. So here the people are the pigeons, and then 12 months are the pigeonholes. So is another example, in any set of 6 integers, there must be 2 whose difference is divisible by 5. To see this, regard the 6 integers as pigeons and their remainders on division by 5 as the pigeonholes. So let's give something very, like something more interesting example. So recall example 19.2 says that prove that if n plus 1 numbers are chosen from the set which contains 2n elements, there will always be 2 of the chosen numbers that satisfy or like that differ by 1. Okay. So prove that if n plus 1 numbers are chosen from the set, there will always be 2 of the chosen numbers that differ by 1. So this is not necessarily true if we choose only n numbers. For example, we could choose the n numbers. Yeah. For example, we could choose the numbers 1, 3, 5 up to 2n minus 1. So they are not actually differ by minus 1. Sorry, differ by 1. So we can actually answer this. So this becomes very easy when we use the pigeonhole principle. So let's say define the pigeonholes to be the n sets so that could be 1, 2, 3, 4, all those which are differ by 1, 2n minus 1 comma 2n. And since we are choosing n plus 1 numbers, each of which belong to one of these pigeonholes, the pigeonhole principle tells us that 2 of them must lie in the same pigeonhole, and these 2 will differ by 1. Between each a. So let's write whatever I said. So since we are choosing n plus 1 numbers, and each of which belong to one of these pigeonholes, then the pigeonholes tells us that 2 of them must lie in the same pigeonhole. Okay, and these two will then differ by 1. Perfect. Okay. Now, we'll discuss another topic, which is inverse functions. So what are the inverse functions and how to find the inverse of a function? So let's say we have given a function f, under what circumstances we can define an inverse function. So basically, to define an inverse function from, we need that f to be onto and f to be 1-to-1. And then we can define it. So let's give a definition. We say that let f from S to T be a bijection the inverse function of f is the function from T to S that sends each T in T to the unique S in S such that f of S is T. Okay. And we denote the inverse function by f inverse. We denote the inverse function by f inverse, that is T to S. Thus, for S in S, comma, T in T, we can write f inverse of T is S if and only if f of S is T. Okay, and as a consequence, we have f inverse of f of S is going to be S, and f inverse of f of T is going to be T. For all S comma T in S in S, T in T. Okay. Perfect. So let's give an example. This is going to be 19.31. So the function which we have defined before as a bijective function, which is a function from f a b c to a b c, with a condition that f of a is b, f of b is c, and f of c is a. then f is bijective, then f is bijection, and inverse function f inverse which will be again from this set to this set, sends everything back to it came from. So f inverse of A is C, f inverse of B is A, and f inverse of C is B. Okay. Number 2, we define a function from R to R by f of x is 8 minus 2x for all x in R. Then f is bijective or a bijection, and f inverse of t is nothing but 1/2 8 minus t for all t in R. How we know this? How we know this? So to know this, so how to find this inverse function? To find this inverse function, we need to write this. F of x is t, then t is 8 minus 2x, 8 minus 2x, then replace, find the value of x, find the value of x, and that is going to be t minus 8 is minus 2x, and if you multiply the minus both sides, you will get 2x is minus t plus 8 is 2x, and then you can say x is going to be 1/2 8 minus t. Okay, now you can say, just replace the values. That now f inverse of t is nothing but 1/2 8 minus t. Okay, that's how we find the inverse function. Okay, perfect. And we will talk about now the composition functions. So we will know that how to compose two functions. So a definition. Let there are three sets and let there are two functions okay, the composition of f and g is the function g compose f, which is a function from s to u, define as follows, that g compose f of small s is going to be g into f of s for all s in s. So you can say g of f is a function of a function, which is a phrase you may have seen before. It's a function of a function. So you can say it as g of f is a function of a function. Okay, perfect. Let's define it by example. (19.4) says that we have a function f from R to R, given by that f of x is sine x. We have a function given g from R to R again, given by that g of x is x squared plus 1 for all x in R. Then g compose f of x is nothing but g of f of x, and that is that g of sine x, and that is sine square x plus 1. Okay, similarly, f compose g of x is f of g of x, and that is f of x square plus 1, and that is sine x square plus 1. Okay, similarly, we can define compositions. So note that if f is a function from s to t is a bijection, then there exists a function inverse. Then there exists an inverse function, which is t to s. And if we compose f and f inverse, we get that f inverse compose f of s is nothing but f inverse of f of s. And this is s only. And f compose f inverse of t is t again with the same rule. Okay. So this means that f inverse compose f is nothing but identity function of s, and f compose f inverse is nothing but identity function of t. Okay. Then we have another proposition for this, that when the composition functions are one onto and bijective. So we gave proposition 19.2, in which we say that there are three sets and there are two functions. Then 1 if f and g are both 1 to 1, so is g of f. 2 if f and g are both onto, so is g of f. 3 if f and g are both bijections, so is g of f. Perfect. You can prove this. So for 1, if f comma g are both 1 to 1, then we take for two small s inside the s set, we see g of f of s1 is g of f of s2. Okay. Then we say g of f of s1 is g of f of s2, but this is nothing but f of s1 is f of s2 as g is 1 to 1. Then s1 is and s2 as g is, sorry, f is 1 to 1. So g of f is 1 to 1. Okay. 2, we suppose f and g are both onto, then for any u and u, there exists some t and t such that g of t is u as g is onto, and there exists some s and s such that f of s is t as f is onto. So hence g compose f of s is going to be g into f of s, which is nothing but g of t, which is nothing but u. Showing that g compose f is onto. Number 3, this follows immediately from parts 1 and 2. And we have proven the proposition. Now we will give the last kind of thing in this chapter, and that is something about counting functions. So there are functions which we call them counting functions. Okay, so how many functions are there from one finite state to another? This function is quite easily answered. Like this question is quite easily answered using some of our counting methods from chapter 16. So let's give a proposition. (19.3). We call that let there are two sets S and T be finite sets with the condition that order of S is M, order of T is N, then the number of functions from S to T is equal to N power M. Okay, right? And we can prove this using the information from the chapter 16. So let's say we have a set S which has M elements. We define a function f from S to T is defining a function from S to T is an n-stage process, is an m-stage process. Perfect. Stage 1 is we choose f of S1. This can be any of the n members of C. So the number of choices is n. So we choose f of S1, and this can be any of the n members of T. So the number of choices is n. Stage 2, again choose f of S2. So again we have n choices and so on up to stage M, where we choose f of Sm again, and choices, right? Thus, by the multiplication principle 16.1, the total number of functions is the product n times n times n, that is n power m, because n is multiplying with itself m times. Perfect. And here we will end this chapter. Thanks so much. Bye. Please like and subscribe and share whoever wants to learn something about the pure maths and its basics. Because after this, I'm going to talk about some very important subjects like group theory, ring theory, field theory, abstract algebra in general, commutative algebra, non-commutative algebra, something like that.